So today I will present time-resolved dynamics of textures, magnetization textures with curling of magnetization. So what is curling, if you don't know, is the tendency of magnetization distributions to close their flux due to magnetostatics. And it is a very old concept introduced originally to explain the Brown paradox, why coercivity may be much lower than anisotropy field in large magnetic systems. So it is very relevant for 3D nanomagnets because magnetostatics is long range and in general is larger in bulk-like with 3D shape materials. And a textbook case we have already heard of is cylindrical nanowires. An example of curling texture that you have is found at the end. Okay. I will go old style. Is found at the end of the wires, which is called an end domain. And here you have longitudinal magnetization and curling of magnetization just on the periphery if the diameter of the structure is somewhat larger than the dipolar exchange field. In principle, it is often found that it is 7 times the dipolar exchange field. I will discuss a lot also about domain walls, and I present here what has been discussed already, the Bloch point wall, occurring in the case of head-to-head magnetization. And in the Bloch point wall, you have a circular curling of magnetization on the periphery. And for continuity reason, magnetization cannot be defined somewhere in the bulk. And in practice, it is on the axis. And this is called a Bloch point, already also a very old concept. So curling, I have introduced. One word about chirality, which I will try to use correctly. So a chiral system is a system that cannot be superimposed with its mirror symmetry. So that requires that you are 3D, or for instance 2D with an oriented surface, can be by curvature or by stacking. Okay. So for instance, the end curling is chiral because you have longitudinal magnetization and clockwise or anti-clockwise. But the Bloch point wall is not chiral. Okay, sometimes it is called chiral. Bad luck today. Okay, because here you have a mirror symmetry. Okay, because you have head-to-head magnetization. It is chiral in dynamics because it moves left or right, but in static conditions, it is not a chiral object. And there are also some dynamic non-reciprocity, but I will not discuss this. And in magnetism, based on electromagnetism, we are chiral due to the vector product here. And for instance, the Ørsted field is chiral. You have the current, and the B magnetic induction field is clockwise with respect to the current, which means that the Ørsted field that you will necessarily have in 3D nanomagnets, if you want to make some spintronics, will directly interact with chiral magnetization textures. And for some time, the Ørsted field has not been considered in simulations, and only in late times, people have started to wonder what can happen. And in this case, studying the assistance of nucleation with the Ørsted field. And in the experiments we showed a couple of years ago that you have an impact on the Bloch point walls, selecting the circulation right or left of the Bloch point walls dictated by the Ørsted field. And this is one of the topics I will describe. So a short word about fabrication. Many has been introduced by Amalio this morning. In our case, we use porous templates in alumina. And out of the various techniques to fabricate wires, we will use electroplating. And of course, we free the wires from the template to be able to contact them electrically and image. And in a number of cases, you can introduce modulations such as diameter or material. And of course, more broadly, you can fabricate nanotubes or core shell. So first, I would like to discuss the impact of Ørsted field on domain walls. So here is an image of, so it's a photo emission electron microscopy image. I do not enter into the details. You have a wire, the length scale, and here you have 3 domains. Black, white, black is related to head-to-head or tail-to-tail. Okay, so it is the same. But if you notice, you have a slightly different contrast at the domain walls. And this informs you, if you analyze this, about the domain walls, the type, and possibly the circulation. And what we have, depending whether we apply a current negative or positive, we show that we have always Bloch point wall and that the circulation is dictated by the Ørsted field that was associated with the current. Okay, so there is a striking difference in terms of physics, whether you try to affect the domain walls with magnetic field or spin polarized current. And we have to consider the role of the Ørsted field. So this is an example of the existence of the Ørsted field. So this is an experiment performed by scanning transmission in X-ray microscopy. This was at SLS in Switzerland. This is the static image. In that case, it's a cobalt nickel wire. And this is the sequence that we sent: negative pulse, nothing, rest, positive pulse. And you see during the positive or negative pulse, you have a black-white or white-black contrast. And as the beam is coming perpendicular, this means that starting from longitudinal magnetization, you had some switch tilting like this or like that under the stimulus of the Ørsted field. In that case, we had some technical problems. We could not do some switching, but in other experiments, we made some switching. And what we found is that depending on the strength of current that you sent in the system, you have a threshold, either no switching, circulation remains as it was, or you switch into the direction of the Ørsted field. And it is really 100% success, so it is very well defined. We can reproduce this with simulation. We see that we have 2 stages. First, a very fast shrinking of the domain wall, and then something happens that I will describe afterwards, which leads to the switching from, so this is the surface map. This is longitudinal magnetization. It is unrolled, and this is the peripheral magnetization. And so you can switch from positive or negative to positive. And we predict with analytics that this threshold current should vary like 1 over the radius cube. And the physics is very simple. The cost in exchange of curling varies like 1 over r squared. And the impact of the Ørsted field varies like r, because you have more current inside. And so the efficiency should vary like 1 over r cube. And if you plot the simulation, the critical current versus 1 over r cube, you indeed see something which is linear. And there is a quite good agreement between the values in the simulation and the experiment. If you look what happens for reversal, it is quite funny. So this is again unrolled maps with head-to-head magnetization, and this is the peripheral magnetization. And the color code is the radial magnetization. At the beginning, because you are head-to-head, there is a slight out of plane. That means radial magnetization because of magnetostatics. And after some point, you see that you have some areas which reach radial magnetization, which is -1. And then it splits and evolves into a set of vortex and anti-vortex, which means that in the bulk, you have a vorticity loop. And after some point, you see that these split apart, and this switches from blue to red. And the physics is quite simple. This loop will propagate into the bulk, meet the Bloch point, and as the Bloch point is head-to-head, if it moves along this vorticity tube, it reaches the surface, it switches the radial magnetization. And so here you get the red. And this red again evolves. At some point you have another nucleation. And so when a red meets the blue, because of the head-to-head, again, when they annihilate, it will create a Bloch point that enters again, but now with the opposite circulation. So it's a rather complex microscopic situation, but in the end, there is a similarity between the transition between a coherent reversal in a nanomagnet and incoherent. Okay, here you have a system, the periphery is hundreds of nanometers. So instead of everything going radial, which would cost a lot of energy, you nucleate somewhere and you propagate along the perimeter. But you also have to consider the bulk. And I do not enter into details, but you can follow the different objects, the vortex, anti-vortex on the surface, the Bloch point inside, and link topology inside and outside for conservation. So the funny thing now, you can make some time-resolved measurements. This was done in Bécy. And for instance, this is as a function of the length of the pulse. And here you see that it is differential imaging. So the domain wall shrinks, but the pulse is not long enough. And then when you remove it, the domain wall goes back to its initial size. But after a given threshold, in that case, it is 2 nanoseconds. In fact, the domain wall shrinks, okay, and it takes time even after you have stopped the pulse. And then it merges, and you have the final switching that I have shown previously. Okay, so we do not resolve this vortex anti-vortex. Probably it is stochastic, but at least we access the time scale. So this is the snapshots. So you can really derive, for instance, the width versus time. And our hope is that we can have a direct determination of damping in a complex spin texture, okay, which is a really fundamental physical question. How much time do I have? 10 minutes. Wonderful. Okay. So this is one example on domain walls. And now I will come to the case of wires which are modulated along their length. So it has already been presented by Amalio how to do this. You can have a bath. For instance, you have 2 metallic soles. And if you change your pulse, the voltage of electroplating during certain time, depending on the electrochemical potentials and the concentration of the 2 soles, you can make different compositions. And this is an example by our colleagues who are really expert in this in IMDEA Madrid. So this is a transmission experiment at the iron edge. So when it is darker, that means more photon absorbed. That means the composition is higher in iron. So in that case, it is permeloid segment and iron-rich inserts into the structure. So to some extent, you can control the length of this modulation by the length of the pulse during electroplating. And the idea, of course, is that if you dream to make a memory out of this, you would like, as Stuart showed, to have specific locations to have the domain walls, okay? Not to have domain walls that wander, and in that case, it would no more be digital. So if you do the simulation about this, so will it work now? Yeah. If you do the simulation, you see that at the modulation, you have a bit of curling. It is not 90 degrees, but it tilts. And if you make the experiment, you have the absorption with the modulation. And indeed, here you have some curling of magnetization, which can be white-black or black-white. And the physics is quite simple. If you had uniform magnetization, in that case, because of the mismatch of magnetization, you have planes of charges, okay? So magnetostatic energy. What happens if you make some curling is that you create some volume charges which tend to screen the 2 planes of charges. So instead of having a dipole, you have a quadrupole, and you decrease the magnetostatic energy, of course, at the expense of exchange, because you have to rotate magnetization along the length. And again, in these structures, so here is an example of modulation, image after a positive or a negative current, and magnetization is always uniform. Okay, there is no domain wall here. You can switch from white-black to black-white. That means you are able to switch the modulation this way, or that way, clockwise or anti-clockwise. So again, we try to have some time-resolved measurements. So what we do, always the same, some rest to make some imaging, and also to allow the wire to cool, because we are sending pulses with density of the order of 10 to the 12 amp per meter squared. So you see it is black and white, and during the pulse, you will see that with the state, you will see white and black. So let us wait a few seconds. Okay. And when you stop, when you stop the pulse, you see that the modulation has switched. Okay. So this is the snapshots. The figures which are shown here is the time difference between two images. So be careful here, it is 50 picosecond. And in these two rows, because the process is slower, I have put 200 picosecond. And this is for different strengths of current. This is a high current. And we see that here we switch in about 100 to 200 picosecond. And in fact, this is, in fact, this is not, probably not the real physics. It is limited by the rising time that we can send of the current to the sample. And if we decrease the current, at some point we see that we have a slowing down. Here it takes maybe 300 picosecond, and here it takes close to 1 nanosecond. And in fact, this happens to be the threshold. Okay, so the time for switching, like many switching processes in magnetism, diverges when you go towards the threshold. So we are trying to reproduce and understand this with simulations. So to match the experiments, what we do is really make a ramp of current, and also this avoids to kick magnetization out of equilibrium very fast. And this, anyhow, does not occur in the experiments due to the rise time. These are the parameters that we use. And this is an example that we show here. For instance, in a few hundreds of picoseconds, indeed, with the densities of current that we use, we are able to switch the circulation in these systems. And when we plot the inverse switching time versus the strength of current, in a usual switching process, we have something which is linear. Here it is not linear, and we believe it is due to the fact that we have these two ramps, and then we just decrease the plateau. So the physics is more complex here. But anyhow, we have a divergence of the switching time. It is 1/time when we go closer to the switching threshold. So complexity here, we find some discrepancy between simulation and experiments, that we have some uncertainty in the evaluation of current that goes through the structure. It's always tricky. We cannot measure it directly. We also have some uncertainty in the length and perfection of the modulation. And we also have some uncertainty in magnetization and exchange, because iron nickel is very nice, because the electrochemical potential are different. We can make these modulations. But you may know that when we go close to a given concentration of iron, then you have a collapse of magnetization and ordering temperature. And we are not so far, so any small variation in composition will have an impact on the value of MS and exchange. So this can partly explain the difference that we have. And we have also probed the effect of heating on this system. This is the excitation I have shown before. You can use this type of excitation so that you send, or for instance here, you send a pulse here, which will hit the sample, but not switch, because you apply it in the same direction as you have switched before. And depending on the strength and width, you will hit, and then you will probe with a switch right afterward. And this is the two situations. With no heating, you have a threshold which is slightly larger. And this is, if we put some very simple model, this is something that we expect. But this is not completely obvious, because if you have lower magnetization, you also lower the Zeeman torque from the Ørsted field. And so this is my last slide. The conclusion here for the modulation is that we can switch probably much faster than 200 picoseconds if we are able really to send very short pulses. And this very short time scale is not a surprise. For instance, in this pioneering experiment, switching within a few picoseconds was obtained on thin film by having magnetic field up to 250 millitesla in precessional switching. And also on domain wall motion on the magnetic field, if you put the precessional speed, is of the proper order of magnitude. So we do not pretend at all that we will make some memory, but again, it is very funny that we are reviving concepts like the ferrite core memories that were used really in computers, in memories in the early days, and we are nowadays playing with very small things. So in a sense, it is new, but in other sense, you see that culling or non-homogeneous magnetization or this flux closure domain, many people have worked before and made very nice things. And I will stop here. Thank you very much.